for the introduction. Yeah, so I'm Giovanni from the Crowd Lab, and I will be talking about some work that we've done to revise the graph law model that is used to account for ganglion cell displacement. So as probably many of you involved in glaucoma research or structure-function relationship studies know, we can get quite a good amount of details from structural measurements of the damage caused by glaucoma to the inner retina. So for example, here on the right, you have a map of ganglion cell thickness in a glaucoma patient. And we can also have a good amount of details on the functional side if we use specific tests that have a very high density sampling density like the 10-2. So, and if you look at those, the two maps grossly overlap. So one might be tempted to simply invert the visual field and overlay that on top of the structural maps. But you might also know that this is quite inaccurate, especially in the parafoveal region. And the reason is that the ganglion cell layer, the ganglion cells that receive the stimuli are often displaced radially from, well, not often, they are always displaced radially away from the fovea. So, and this has important implications because, for example, if we shine a stimulus on this part of the retina, the ganglion cells that will receive the input from the photoreceptors will be displaced radially away from where we are projecting the stimulus. And as you can see, this connection is performed by the Henle fiber layers, by the Henle fibers, which have this diagonal path from the photoreceptor to the ganglion cells. It has now become much more commonplace to account for this displacement, especially after the work that has been done by Hood and colleagues. And right now, a lot of commercial devices also use this account for this displacement, and this is often named the Hood report. And here you can see a difference from the same example as before. Here, the size of the dots represents roughly the sensitivity recorded at these locations, and you can see the undisplaced stimuli and displaced stimuli, and you can see that in the displaced stimuli we account for the radial displacement of the ganglion cells. Some of you might not know though that this displacement was not first studied by Hood, but actually the first studies looking at this aspect of the retina date back to 1999. The first one was published by Giovanni, and they simply measure the length of the fiber layers in histology sections, and they built a model of ganglion cell displacement and different eccentricities from the fovea. But the one that is more widely used nowadays is the improved model developed by Professor Neville Grasso, who sadly passed away last year. And in 2005, he published this paper that is now a milestone in structure function analysis. And this is the one that we use in almost every structure function analysis of the macula that we do today. So given its importance, so the main difference from the short-strand model was that they used the Henle fiber measurement just to confirm the results, but the model itself was based on a combination of ganglion cell histology and visual acuity measurements obtained from psychophysical tests. And the two pieces of information were combined to obtain the final model. Given its importance, is worth reviewing how the model works. And essentially, the model is composed of two aspects. The first one is a density map of the ganglion cell bodies, which is provided by histology, and this map was created by Crucio and Al in 1990, so a while ago. And the other part of the model is a model of ganglion cell receptive fields as they change, the receptive field density as they change with eccentricity. So receptive fields are essentially the part of the retina that feeds in information to a single ganglion cell. So approximately, well, actually not approximately, exactly, we would expect to see the same amount of ganglion cell receptive fields and the same amount of ganglion cell bodies. And with this assumption in mind, we can now plot for a given sector of the retina that here is highlighted in white, the ganglion cell body density and the ganglion cell receptive field density as we move away from the fovea towards the periphery. So this is the first plot that you see here in the middle panel you can see the plots of density, and in the rightmost panel, you can see the cumulative count derived from this density plot. So as we move away from the fovea, you can see that they start off very different, but then they become much more similar. So ideally, the cumulative counts of the ganglion cell receptive fields, they should match exactly the ganglion cell counts, the counts from the ganglion cell bodies. This, of course, doesn't happen straight away, mainly because the two estimates come from very different methodologies. So some discrepancy was expected. So one of the core aspects of Grasler's work was to develop a method to estimate this parameter here, the EQV parameter, which was originally set to 2, but then it can be, the good thing is that it can be estimated so that the two curves match where no displacement is expected. So now we can simply calculate from these cumulative count curves, we can calculate the displacement of ganglion cells by simply counting the horizontal distance between the two curves. So the original model had some limitations that mainly it was calculated, the two main ones were that it was calculated for only for the 4 principal meridians, and of course they needed to use a schematic eye to convert from visual degrees to millimeters of the retina on the retina, and they used just an average schematic eye. These are not limitations of the model itself, so these are the aspects that we try to improve on in our work that we did to improve the model. So the first thing that we did, we tried to rebuild the schematic eye that they originally used for the model. And as you can see, if you cut the cross section through the model, you can see the different components of the model. Mainly, this is made of just a layer for the cornea, a lens, and then the retinal sphere, which includes the retina and the sclera. The main thing that we had to change was the radius of this retinal sphere, and the reason was that these had to match the retinal sphere assumed for the histology database from Kusho and Allen, published in 1990, which used a different schematic eye. So we tried to match them as close as possible, and this discrepancy was actually a limitation and a problem in the original Grasler model. So we fixed that, and that was the main fix that we had to do. The other thing that we accounted for with this schematic eye was the change in the projection of the stimuli with different axial lengths. So for example, here you can see that for longer eyes, the projection of the 10-2 depicted in this schematic will be a bit more spread out compared to what you have in shorter eyes. So this needs to be taken into account. Another assumption that we made with this global expansion model was that the retinal would stretch equally in all directions with the axial length. And we needed to check on this assumption. And to do this, we basically measured how the profile of the ganglion cell layer changed with different axial lengths. And we used 265 LTIs from the Northern Ireland Sensory Aging Study, kindly provided by Dr. Ruth Hogg from Queen's Victoria University. And essentially what we did, we measured the major and minor axis of this ellipse fitted to the ganglion cell profile. And we observed how, after correcting for ocular magnification, we observed how it changed with axial length. And you can see that it scales quite well following a geometric scaling, so a global expansion assumption. So we use this assumption for the rest of the model. So with all of this in mind, we can now plot we can now estimate the value for the EQV parameter for any given meridian, and we can build this for any given axial length, and we can produce a displacement map for any given meridian, and this can be changed for different axial lengths, which is what we were trying to do. One other aspect that we needed to explore was how to apply this displacement to perimetric stimuli. And this is very important because one might be tempted to simply shift the location of the stimulus where the receptive ganglion cells would be. But actually, this does not account for how the anatomy works in this region, because ganglion cells and photoreceptors closer to the fovea will be connected by shorter Henle fibers compared to photoreceptors and ganglion cells that are further away. So essentially, the projection in the ganglion cell space will be slightly distorted due to how these connections change in a short range of eccentricity. Unfortunately, many of the papers that have been published on the topic use simply displace the location. So here you can see what this would look like in a Goldman 4 stimulus, and here you can see the undisplaced 10-2 locations, and here you can see after we have applied the displacement. But actually, we're going to call this one method 1. Actually, what we propose should be more correct is this displacement map, which instead takes each point on the edge of the stimulus and changes its location based on the Russell model. So you end up with these ovoidal shapes that are slightly distorted according to the model. So we can easily check which one is the correct one. So here, because we know that within the same area on the retina, we should expect the same number of ganglion cell receptive fields and the same number of ganglion cell bodies. So if one of the methods is correct, we should expect to see the number in a graph like this, where we have the ganglion cell receptive fields on the horizontal axis and the ganglion cell bodies on the vertical axis. We would expect to see all the observations lying on the diagonal line of equivalence. And we can see that if we apply method 1, we don't get this result, and essentially most of the estimates are severely distorted, especially in the parafoveal region where you have the highest count for ganglion cells. If we instead apply method 2, you can see that this fits quite nicely with our expectations. So we can show that this method 2 yields consistent calculations. We also confirmed this with a separate data set of 28 volumes counts from 28 healthy subjects less than 40 years old. And we basically obtained the same results. The only difference is that we have a bit more noise, because these are actual data derived by converting the ganglion cell thickness map that you see here into an estimate of ganglion cell density. So some noise is expected, but essentially we see the same results reproduced with real OCT data. So you might say, well, wait a second, this sounds awfully complicated, but luckily, and it is, but luckily for you, we have developed a shiny app that is very user-friendly, and you can find it online at this address, and you can plug in all your data, and it will give you all the counts at different locations of the retina, and basically all the measurements that we use for this presentation will be available to you for your data to use. And we hope to help you with your research, and also help standardize how we do these calculations in different structure function analysis. I would like to thank all my colleagues that helped me with this work, especially my colleague GiovanniMontesano and Ruth Hogg for providing the data, and also Professor Gawé Heath and Professor David Carr for mentoring, and all my colleagues from the lab. Thank you very much. I'm done.
Thank you very much, Giovanni. That was great. Let me just quickly switch off my timer so we don't get interrupted by it pinging at me. So I've just got a question for you, just while I'm waiting for a few questions to come through. So given this model, do you think we could use this to help inform better parametric stimuli? Do you think that it would be useful for something like that?
Yes, in the sense that the hope was that we could, well, actually we have done some work on this. Basically, you can use ganglion cell estimates to account for where the stimuli would be located to detect damage, and also what count and what sensitivity you would expect from at each given location, given the structural map. The other thing is this is the first step into exploring the correlation between ganglion cell numbers and ganglion cell and sensitivity. So, for example, it would be very useful for analysis, for example, relating the size of the stimulus to the number of ganglion cells that are being stimulated. And actually, there has been some work done in, I think it was published in IOVS, and actually we compared our results with that work. And essentially, one of the problems was that they used method 1, and all their measurements were completely off by at least one order of magnitude. So I would say it will improve because it should provide more accurate measurement for what we want to investigate. So not directly, but certainly this is an essential methodological step to get right for any conclusion to be valid. And this doesn't seem to have been the case in some papers that have been published so far.
Fantastic, interesting, thank you. We've had another question through, which starts off by saying superb work, so well done. Is there any way of building in OCT data into this model so that you're using real measures rather than estimated measures?
Actually, these measurements, these ones you're seeing here, are thickness measurements from ganglion cells. So if you want, and actually this is a feature on the app, you can upload any structural measurement. Of course, it has to make sense because this is meant for the inner retina. So if you're using, for example, any thickness measurement from ganglion cells in a plexiform layer or a retinal nerve fiber layer, you can calculate the average thickness, for example, or even reflectivity. So we have an example in the tutorial that we provide with the app where we show that you can use this method to calculate the amount of RNFL reflectivity within the display area. So yeah, I would say so. The only reason why I was talking about estimates was because when you convert from ganglion cell thickness mass to ganglion cell density, you estimate that based on the thickness that you measure. So the actual measured value is the thickness, is not the final estimate of density, which is obtained by combining the thickness with the database provided by Kushner and Allen. So it's still an estimate if you want to refer to ganglion cell densities, but if you just want to use any other structural outcome, you can just use any regular measurements that you're used to.
Fantastic, thank you very much. A really thought-provoking talk, thank you. Okay, that's the end of the session. So just to say a huge thank you again to all three of our speakers. It was another great session. And just to remind you all that the next poster session is starting at 12:15. And also don't forget our final keynote at 1 p.m. today. I hope you enjoy the rest of BCOVS.